Okay, moving on to question 19 of Carbonyl's compound tutorial. It's a stretch question. Now we have this periodic acid, which is something new to you. You have not seen this before. Right? Basically what it says is that it splits alcohol with two adjacent hydroxy group into two carbonyl compounds. So if you take a look at this reaction, what essentially has happened, right? You have this fragment here and this fragment here, which becomes a carbonyl and an aldehyde. So in this case, HiO4 must have broken the CC single bond between the two adjacent hydroxy groups, right? So they show you some mechanism, again good for us to take note of this, and then largely you realize that it's going to form this intermediate, alright? Essentially, if you take a closer look at how this reaction proceeds, this H, and one of the O, it's gone, right, as water. Right, so if you do a tracing of this, right, just simple pattern recognition, right? This remains intact. The alcohol group here, okay, remains as it is, right? And so far? Okay, so with that, let's take a look. Now we have this particular compound. We're supposed to draw in figure 17.3 what happens to, what's the cyclic intermediate. So basically pattern recognized, right? So we have a double bond O instead of a OH. So what does a double bond O do? A double bond O, alright, in which the carbonyl is first converted into a diol. Okay? So first of all, the carbonyl is being converted into a diol, which means it's first converted into an OH and an OH. Okay? So that's why it does first. Also oxidized hydroxycarbonyl and dicarbonyl groups by a hydration equilibrium, in which the carbonyl group is first converted into a diol. So this is what it means. A carbonyl converted into a diol. And then you can basically apply what we just did here, right, into this context. Alright? So basically, again, let me zoom out a little bit so you can see the pattern involved. This green hydrogen and that of a double bond O will be gone. So let's try to draw the compound out first. First of all, we have OH, O, O. So this is the fragment from your alcohol, right? And then we form the bond with your I, double bond O, OH. Okay, so this will be like the cyclic intermediate, right, as you can see. Okay, that's how we can systematically get answer. Then, of course, the question wants you to predict the organic product of the reaction shown in figure 17.4. So how can we then get the product? To understand how to get the product, we need to understand how the arrow pushing works. So before we go into that, let's take a look at figure 17.2 to get some better idea. First of all, all of us must agree that this carbon-carbon bond must be broken, all right? Because earlier in the context, we say that, you break up this carbon-carbon bond to get two fragments, right? So this carbon-carbon bond breaks. To show bond breaking, arrow starts from the bond, points away from the bond. This IO bond must also break. Why? Again, because you must come up with two carbonyl compounds. So this two oxygen bond, iodine oxygen bond must also break. Alright? So as a result, the arrow pushing is as such. So we try to repeat this pattern and see if we can get this compound over here. So we repeat the same process. This IO bond, this CC bond breaks. This OI bond breaks. Okay, and then we end up with OH then we get double bond O, right? Because these two electrons goes over to this oxygen. And then for the bottom one, we end up with 1, 2. Okay, let's try to draw it properly. 1, 2. Now we have a double bond O. Right? And that's how we get this structure. Now, of course, last but not least, we have our I, double bond O, and a OH. Right? Okay, so yes, true enough, we can get the structure. So now we are able to understand this. We can then apply our concept into figure 17.4. So of course we have a diol. So now we can realize that we have two diol. So we can do it step by step. We can do this first, for example, before doing this. All right. So first of all, we get a double bond O here. This is where this fragment here is just right. And then we're going to get this other big chunk of things, right? So we have a double bond O over here. So double bond O. And then we keep the rest the same. All right. So that's the first thing we get first. But this, again, we know that this is equivalent. We say that this is equivalent to OH and then OH, because we know that the ketone aldehyde can be converted to a diol. That's what the question says early on. So again, we can then undergo a breakage over here again. And then once we get a breakage over here, we get a carboxylate acid for this fragment here. Right, so carboxylate acid, COO, double bond O, OH, and then a aldehyde over here. All right, so that's how we systematically get the structure. Again, these are not reactions that you've learned. It's largely through understanding the earlier context given. So last example over here, first of all, we have a ketone again. Best if we convert this to OH and then OH. That's what's given in the question. We convert it to a diol. So first thing first, we know that this CC bond must break. Right? So we do get a carboxylate acid on one end. Okay, so let's count number of carbons. 1, 2, 3, 4, 5, 6. So this is my carbon number 1, carbon number 2, carbon number 3. Alright? Then 4, 5, and the carbon number 6, because of the OH with an R group, it will become a aldehyde. It becomes a double bond O. Alright, and that's how I get the structure of this compound. So over here, this OH here becomes a double bond O. The rest of this OH with this chain group remains pretty much the same, right? OH with this remaining chain group remains pretty much the same until carbon number 5. Then carbon number 6 on this hand has a single bond OH, and therefore this becomes a double bond, and that's why it becomes an aldehyde. Okay, with that, we're done with this stretch question.